But this still doesn't really explain, if we go back up, why we get this colorless gas in the brown solid. Now, obviously, the brown solid is just going to be your copper. So brown solid is the solid copper, and this colorless gas. Now, we're not really sure what this could be, right? Okay, so in terms of gases, we either get it being oxygen gas, or it can be the hydrogen gas that we discussed earlier. But between these, they're both colorless. We don't really know. Now, in order to produce colorless gas, we can look at the equation given, and you'll note that in order for gas to be produced, this entire equation has to be reversed. So it would be, for example, like H2O to 4U minus, so on to your O2. This then means that this is going to be it's going to be oxidized, and that would then mean that the aluminium would have to be reduced, and that doesn't, we can see from this reduction potential that's basically never going to happen. And also, if we were to calculate it, it'd be negative 1.23 minus 1.68. So that wouldn't be possible at all. And so we can turn our attention to the other colorless gas, which is hydrogen gas. And this one makes a lot more sense. So we write out the equations for both. What do we get? First equation is just your standard one of Al coming and producing your 3 plus ion and your 3 electrons, and then the reduction, so this is going to be your 2H plus and 2 electrons to form H2 gas. Right, and so remember that this one is 0 and this one is plus 1.68. This is going to be E red plus Eox, since I've already reversed the oxidation reduction potential. So therefore the E cell here is going to be plus 1.68 volts. Again, this reaction is spontaneous. And what we can conclude then is that H2 gas is the colorless gas. So that's 2 out of the 3 parts done, and the final step is going to be around this potassium permanganate reaction. So, okay, if we go back up again, now you're adding this potassium permanganate, so therefore we know that this equation is 100% going to be used, and it's going to start from this side. So this is going to be the reduction. And now we just need to find, so what's the oxidation reaction? And we get a pale green gas. There's only one gas that can be, and that's going to be your chlorine gas. So therefore we already have our 2 equations. That's just going to be MnO for minus 4H plus 3E minus to form MnO2 plus 2H2O. And it's going to be the reverse reaction, so we get 2Cl minus to form Cl2 plus 2E minus. So then we need to make the one balanced final equation. So again, this is going to be times 2, and it's going to be times 3 to balance out the electrons. So balanced equation is this. And the E cell is going to be your reduction. So that's 1.69. And that's going to be minus 1.36 plus 0.33 volts. And the brown solid is going to be your manganese dioxide, and pale green gas is going to be chlorine gas. That's sub-problem B done. And moving on to part C. Okay, so first thing to see here is quite clearly going to be your standard acid-base question. So most obvious thing that we can see is one that is going to be this buffer solution. And we dissolve methyl ammonium chloride into this methylamine solution. And so we want to find the initial and final pHs of the buffer solution. And this final part is just kind of stemming from finding the pH of the final buffer solution. So in terms of approaching this question, we can see here we're given the molar mass, we're given the mass. So so from that, it's pretty easy. We can just find the moles of methyl ammonium chloride. I'm going to just denote that as MaC. So again, using the formula mass over molar mass, so 0.1918 over 67.5. That gives us 2.841 times 10 to the power negative 3 moles present. And we also need to find the base. This is volume, that's concentration, so moles equals CV. And remember to convert into liters or decimeters cubed. So this is going to be 0.025 times 0.05, giving us 1.25 times 10 to the power negative 3 moles. Now, from here, there are different ways to then find this initial pH. You can obviously go ahead and use your Ka, rearrange the equation, but that's many more steps, pretty easy to make mistakes. So the best way to do it is using the Henderson-Hasselbalch equation, which is this. So pH equals pKa plus the log of the conjugate base over acid. And it's going to be the concentration of the base of acid, but obviously here, this is in the same solution, so we can just use moles as, accounting for the volume is just going to cancel out eventually, so it doesn't really make a difference. We're given pKa is 10.64, so it's going to be plus log 1.25 times 10 to the power negative 3 over concentration of acid, and that gives us 10.28. The reason that it's just kind of like this is because CH3NH3 plus is a conjugate acid. So you can set up this equilibrium here if you are confused, and you'll see that this is a conjugate base. This is the Bronsted-Lowry base. It's this proton acceptor, and CH3NH3 plus is going to be your conjugate acid. Now, so this is too high. There's too much base, so we need to add acid to cancel that out. And let's just find moles of H plus that is going to be added from the strong acid, meaning it's fully dissociated into H plus ions. Again, just concentration times volume, which equals 4.15 times 10 to the power negative 4 moles. Now, when we add this extra solution, there's two things it's going to do to the acid and the base. So one is it's going to react with the base, meaning that you get less of it. but 2 is going to add to the conjugate acid. And I think you need this intuitive understanding in terms of acid-base equilibria. Obviously, you can draw ice tables, but I really wouldn't recommend it as it's kind of just it's a bit of a waste of time. Just know in these buffer questions, when you have this buffer, right, it's within like the same power of 10, or just any buffer in general. When you add this extra strong acid or strong base, you need to add it. So if here, if a strong acid, you add the extra moles of H plus to the moles of CH3NH2 plus that's going to be produced, and you subtract it from the conjugate base. So what we then get, and if you still don't understand, just think about it like this. So we add this extra H plus here, meaning it's going to react more with this because we had the equilibrium at the start, but we're kind of disrupting it now, meaning it pushes more towards the left if you want to think about it from an equilibrium perspective. But also, as each mole of H plus reacts with the conjugate base, it means you get 1 mole extra of the conjugate acid and 1 mole less of the conjugate base as the conjugate acid forms. So, moles of the conjugate base is going to be initial moles, so that's this. So 1.25 minus the moles added, giving us 8.35. And the moles of NH3 plus final is going to be the inverse. You just add it to the initial moles, and that will be 3.256. Again, so we have our new concentrations of acid and base. Let's just use the Henderson-Hasselbalch again. pKa plus log base of acid which gives us 10.05. And we can refer back to the equation. The buffer solution is 10.00. So no, he didn't actually add enough HCl. We'll just give it a brief comment here. No, not enough HCl was added. And that concludes question 1 for the 2021 scholarship chemistry exam.